Alrighty, welcome back to 105. So, started linked lists, much fun. So, any questions about anything we went over last lecture? We'll be going over more functions to implement for linked lists to make them nice and easy to use. Nope, all right, then let's get into it then. So, well, let's insert 4 nodes onto our linked list then. So thankfully, based off the last lecture, we created a function called createLinkedList, and we had insert front. And insert front, remember, would actually create the node for us. It would dynamically allocate it, so it would malloc it, and then add it to the front of the linked list and modify it. So, given that, if we want to add 4 nodes to our linked list and have the values be 1, 2, 3 in order, well, we would also have to add them in reverse order because we're always adding to the front. So if I want to add 4 nodes, 1, 2, 3, and 4, and have them in that order, I would have to do a bunch of copy pasting and do something like this. So I can change the values, use them, and now if I compile it, I just get warnings that they are all unused values because I don't actually use N1 through N4, but won't affect any behavior if I try to execute it. If I try and execute it, I'll see that my print list works. I see 1, 2, 3, and 4. So everyone okay with that before we carry on? All right, so I had a comment the last lecture of like, hey, well, you know, if I want to be good and make sure I free everything I alloc, well, I would have to do something like, okay, I have to free N1, free N, and free all these nodes I've created. So I'd have to do something like that, compile it, run it. It's not going to affect my behavior, but if I use Valgrind with this, it would now be happy, or it should be happy because I freed everything that I allocated. So if I run it, I can see that all heap blocks were freed, no leaks possible, no problem. But this kind of error prone. Every time I create a node, I have to remember to free it, which is kind of lame. So we can just write a function to free everything for us that can iterate through the entire list and free all of the nodes. So I can create a function and usually give it a name. So we can say it's just called free linked list, and it only needs one argument, right? It only needs a linked list we're going to modify, and it would do it through a pointer. So remember, we made our linked list structure that just contains the head, so we don't have 2 pointers to modify or a double pointer. So we could create this function called free linked list that just takes one argument by pointer, which is the linked list to modify. So I want to go ahead and free every node and also free that linked list structure itself. So if I immediately started off by just, free linked list, then I'm kind of screwed at this point, right? Because I need to go through the whole list, and if I want to iterate through the whole list, it'll look something like this. So if I have a variable that keeps track of the current node I'm looking at, I could initialize it to be linked list head, and then while current does not equal null, I'll go ahead and, like I did before, I will follow all of the pointers. So the next node I need to go to is current.next, and then I can update my current to be equal to free after I'm done with it. So that's how I would iterate through the list. And then here, each time I want to go ahead and actually free all of the pointers. So here, I probably want to also free the thing I'm currently using. So I read the data I need from it. So I read the value of the next pointer, and then I can free current because I'm no longer using the structure anymore, and I update this current pointer to point to the next node, which I've already captured in a variable. If I don't do that, I might have something like I have above here. So this would be a hard to debug problem in our program because, well, if I have a free and then I actually use that pointer and dereference it after, that is technically undefined behavior and bad things will probably happen. Turns out if I do make that mistake and I run this program, nothing bad happens at all. Oh, I didn't call the function. Okay, sorry. So we can now replace all these frees by a call to free linked list. So now if we do this and compile, oh, we got a seg fault because I guess today my computer wants to use that undefined behavior to actually crash. So if I used Valgrind on this, I can see probably it will point me in the direction of where I crashed. So it's telling me where I mallocked it, and then it's telling me if I scroll up to the top, invalid read of size 8, which is on line 53, which is on this one. So likely on your computer, if you run this, this might actually be okay and not crash. On my computer today, it just feels like crashing. So that's, again, our use after free. So in order to fix that, we'd have to do something like this. So we would go ahead, read the head of the list. That's the only data we actually care about from that structure. Then after we're done with it, we're not going to use it again, so we can go ahead and free it. And then we just iterate through everything, free every node, so we don't actually have to, manually free everything ourselves. So if we compile and run it now, we can see that, hey, all blocks are freed now, no leaks possible. And what we're really concentrating on by writing functions is making our main function nice and readable. So now we can see that, hey, we're creating a linked list, we're inserting to it, we're printing it, and then we're freeing it at the end. Don't have to worry about manually freeing it yourself. This is probably the way you want to go about it. And because I don't need to use the nodes anymore, even though this function returns a pointer from the node, doesn't mean I have to use it. So I could just change my program to something like this, nice and concise. So any questions about that? Another good function we could write. Cool, all right. What about removing a node from our list? So say we wanted to remove any arbitrary node from our list. So say we wanted to remove node 3. So it would look, so right now, recall our list or our linked list looks something like this, where the head represents the list. It's pointing to the head of the list or whatever is at the front of the line. Its value is 1, its next pointer is pointing to 2, pointing to 3, pointing to 4, etc. So we're going to try and write a function that, given a pointer to a node, in this case, let's say it's a pointer to node 3, what are all the steps we need to do to actually remove this node from the list? So I'll give you a little bit to think about what we need to do to actually get 3 out of that list while maintaining everything else. So if we just remove node 3 from the list, we should have the nodes 1, 2, and 4. Alrighty, any ideas how we're going to get node 3 the hell out of here? Yeah. So we want to make this next pointer point to 4, right? And that's about it. And just get rid of this one. So we only really need to change one pointer, but we need to change the previous one through. So our big problem here is given a pointer to node 3, we have to be able to find whatever the previous one is. So if we're writing that function, could get a little bit tricky. You might start off by being like, hey, well, I need to iterate through this list, figure out what node I need to remove. So I can just start off by just having my temporary variable called current, which is what I'm currently iterating over. So I could say it's linked list head, and then start while current does not equal null. I can go ahead and at the end of it, update current equals to current next. So I'm just iterating through every single thing. So now I have to figure out which thing I want to remove, right? So if I'm just given the node I want to remove by a pointer, I can just do pointer comparison, right? So if current is equal to, because, well, if their memory addresses are the same, that means this is the node I actually want to remove, then we probably want to do something like, okay, remove this node. So that lets us know like what we actually have to remove. So, so now we need the previous node though, right? So how do I get the previous node, or what is an idea we have so that we know what the previous node is? Yeah? So if I do like in this, so in this current.next, if we have, let's say we have the linked list again, we have 1, 2, 3, 4. So in here, current is going to be equal to 3, right? And 3's next is 4. Before in the if statement. So here? Oh, if current.next. Yeah, so we could do something like this. If current.next equals node, then that means current is the previous node, right? So I'm pointing to the node I want to remove. So, yeah, we could do that. So maybe I add a little comment here. In this case, current is previous to the node we want to remove. Give myself a little bit of help. So if I do that, then all I want to do is simply update current's next. So this is the previous node. So current next is the previous node. So I want to update what? It's next, right? So I have to update current.next. Instead of pointing to the node that I'm trying to remove, I need it to point to what? Current next, or simply just node next, right? So whatever I'm currently pointing to, my next. And then if I want, I can go ahead and do something where I also update, I can also update node.next equal to null, just set it equal to null because I've removed it from the list just to kind of clean it up and reinitialize it. So that look good with everyone? Yeah?
Should we also free it? Free the node?
Should we also free it? It's up to us how we want to write our program. If we want to use that node again, because the pointer to it's still valid. Maybe we don't want to free it. Maybe we do want to free it if we know we'll never use it again. So it's kind of up to us. In this, let's just assume we don't, well, let's just assume we want it to be around. So if I want to test if this works, I could go ahead, call my remove node function. So I want to remove from the linked list. Let's say we want to remove node 3. And then print list again, just to make sure we actually did it correctly. And again, if I want to go ahead and make sure I clean up all my memory, this free linked list just frees everything in the linked list. So I would have to go ahead and make sure that I manually free node 3 because it's not connected in the list as well if I want to free everything. So if I do this, compile it, I'll just get warnings that I have unused variables, which is fine for now. So now if I run it, hey, it seems to work. So can anyone see any issues with this remove node function at all? Yeah. Sorry? So if the node is at the end, what's wrong if the node's at the end?
That we need to link the previous node to null, and there's no node in it.
So if we're removing the last element, then let's see what would happen. Let's say we remove 4, right? It'll iterate through this, and then current next will be equal to node, so current will be equal to 3. And then we'll do current.next, so that would be 3's next, is equal to node's next. And node 4 would just be pointing to null, so I'm changing 3's next to point to null, and then this node to point to null, which should be fine, right? That should be fine. So let's go ahead and try it just to make sure. So let's say we remove node N4. So if we remove N4, run it. Oh, because I have a free here. All right, I'll get rid of that. That was a double free. All right, so if I do that, that works. So not that, but there's still a problem with this yet.
Did you try to remove the first node?
Yeah, what happens if I remove the first node? So let's see. Oops. Go away. So if I try to remove the first node instead of the last node, well, what's going to happen? I run it, nothing changes. Why does nothing change? Yeah.
Checking the next node, so we start with the first node, which is going to compare to 2.
So I start with the first node. So here, if I'm trying to remove 1, so current is currently pointing at node 1. So current does not equal null. And then current next, so 1's next node is 2, right? So I've immediately just skipped over it. So how do I fix my code to actually work now? Yeah.
At the start, you can say if node equals link, if current equals node.
So if current is equal to node,
Do link list head is equal to node next.
and that's it.
I think so.
All right, so we can do that. We can run it, see what happens. Seems to work. Seems to work, but this is actually removing it. So what happened before is, yeah, if we're removing the thing at the front of the list, we actually have to update the head of the list, right? Because there's something new in the front of the list. So that's what this is doing. If we want to be complete, let's say we make sure to set nodes next equal to null. And then at this point, we've already removed everything we need to remove. So we can just type return, because we don't need to actually iterate over the rest of the list if we just removed what was at the front of the list, right? So we could probably do something like that. So if we compile it, we run it, it works. Seems all right. So everyone okay with that? We've fixed our problem. So let's see. No, doesn't. Still no issues or anything like that? All right, well, let's see. What if we do something like, oh no, another good test to do here is if we try and remove the same node twice. So if we try and remove the same node twice, well, depending on how we wrote it, something bad or not bad may happen. In this case, we should be okay because we're always comparing current equal to null, and current is anything reachable from our list. So in this case, it should just go over it over and over and over again and go ahead and check if something in the list is pointing to it. In this case, nothing should be, so if I try and remove it and it's not in the list, I should be okay. So if I compile and run this, seems like I'm okay. So this version is pretty good. So any other questions, comments, concerns about this one? Seems pretty good. Okay, well, so yeah, to remove, we need to know another way we could do it. If this is not the way you're thinking about it, if you want to create a variable if you want to keep track of the previous node in a separate variable explicitly, you could create a variable called previous, initialize it to null, iterate through the list until we find our node, keep updating previous if you want to be really explicit that way, and then once you find a node to remove, well, you know the previous as well, you can just remove it through that pointer. But we stopped one before, which was probably a smarter idea to go. But if we do this, our edge cases are that, hey, if previous is null after the search, this node is at the front of the list. And if node isn't in the list, crashing or doing nothing is okay. So this is one other solution, just so you have it, that explicitly keeps track of the previous. So initially, current can be equal to the head, previous is equal to null. And then to iterate over everything, I can go over and just search for something that matches the current node or the fact that it's not equal to null. So I could just search, like one solution other students have come up with is like, yeah, just search until you actually find the node and don't consider the fact that the node's not there. So we have to account for that. Our solution also accounted for that, but you can combine the conditions that just keeps on looping until either you find the node or you hit the end of the list. And then these are all of our kind of cases here if we write it out like that. So if current equals null, that means we have not found this node in the list. We don't have to do anything. We can return. And if previous equals to null, that means there was nothing before the found node. Then we have to update the linked list head. Otherwise, we have to update the previous's next is equal to the current node's next. And last one, just to reset the node, it kind of separates out my cases so that I always just reset the current node, which is the one I removed and found, next equals to null. So another way to structure it that may or may not be slightly cleaner. Again, up to you. So you could also think of that problem a bit more indirectly. So we could, on the other hand, check the address for values for head until you find the node's address. After finding the address, just update that value to point to that node's next. So this gets rid of the edge case. So basically, throughout this whole thing, you would just have a pointer to a pointer that you want to modify, kind of like the scanf. And then it doesn't matter if you're modifying, so if we go back here, if we're removing the beginning element of the list, right, we have to change head to point to something else. If we're removing an element somewhere else, we're updating the previous's next to point to something else. But at the end of the day, they're both just pointers to nodes. So if we just start off pointing at the thing we would like to modify, then we can just go ahead and iterate normally. And if it's the first element, if it matches whatever head's pointing to, we don't have to do any special case and make sure we update the linked list head or anything like that. So, oops. So this is somewhat, this gets rid of the corner case, but we're adding another level of pointer, which might be very confusing at first. But if you ask the one of the Linux programmer, this is like good taste for linked list because if at all possible, you should not be depending on programming against edge cases. So this is the version that we could write to remove all the pointer checks and all the weird edge cases. So same arguments as before, but now instead of maybe modifying the linked list head, we can create a pointer to a node because we might be modifying what node we are pointing to, and we don't care if we're modifying the linked list head or a next pointer. So to start it off, we would be pointing to the linked list head, and then we could have the same while loop. So while, in this case, we dereference P, that gets the value of the pointer. So if it is not equal to node, so if it doesn't currently match whatever we're trying to find, and we dereference it, it's not equal to null, so it's not the end of the list. This one is a bit ugly, but we could do something like this. So we dereference P. In this case, we have to because it's also a pointer. So this gives us our pointer to a node back. We can use the arrow to access its next field. And then we're just taking the address of it. So we're just updating the pointer to a pointer every time through. And now we kind of eliminate our edge case. So if we dereference P and it's still null after that while loop, then, well, we don't have to update anything. It's not found in the head or through any of the next pointers. And then if I did find it, well, all I have to do is go ahead and dereference P, so this is the previous node that I need to modify, and make it point to the node's next pointer. So I'm skipping it. So you could even make this smaller. If I just remove this if statement, then it will just segfault if the node isn't found. Sometimes you might figure that, like, hey, if you're trying to remove a node that's not in the list, that's invalid. Again, that is up to you, but we could make this even smaller. If we want to protect against segfault, we need to do something like that to make sure that, hey, it's actually in our list if we're removing it. So how this would work, oh, okay. So yeah, this might take a little bit to wrap your head around, but it is arguably nicer in a way, even though it looks slightly ugly. But it is less lines of code, and some people strive to do that for whatever reason. So in this case, if we go back, our P value, or that P variable, is again pointing at what we're trying to modify. So it would initially be pointing at head, and then we'd be checking it by dereferencing it, seeing what heads or what the next value of that node that it's currently referring to is, and then taking the address of that. So we're pointing to this pointer, and then we keep on doing that until we find it. And what we're pointing to is the next field or the head that we need to modify. Again, might take you a bit to wrap your head around, so don't worry about it. But if you can wrap your head around this and argue about it and see that it is indeed correct, you can officially call yourself a C programmer. This is about what we're at. So you can read, yeah, this is about as complicated and as, I would say, possibly ugly as C gets. So if we rewind a bit, we can rewrite some other useful functions. So when we use list, another thing we might want to know is like if a list is empty or the length of the list. So we could try to write both of those. So, oops. So if we try and write both of those, maybe we want to write some other helper functions like, hey, let's write a function called isEmpty that just takes a linked list. So anyone want to help me? How would I write this function called just isEmpty? Yeah.
If linked list head is null,
Yeah, so if linked list head is null, whoops, then return true,
and then return false.
and then return false anyways. All right, everyone agree with that? So this is something I see a lot from beginner programmers because this is a bit weird. This is also kind of a bit strange and believe it or not, more complicated than you need to write because essentially what we have written here is like, hey, if we actually evaluate that condition and go into that if block, it would be something like if true, return true, right? And at the end, if we put in else, return false. Or if it was else if false, return false, which we don't need, right? If this was x, in either case, we can just return x, right? So in this case, I can just make this even smaller because I can just return the result of that Boolean expression. So I can just return if the linked list head is equal to null. So if linked list head is equal to null, that's true. This whole thing is going to return true. I don't need an if condition or anything like that. And if it does not equal null, then it's going to return false, which will give me false. So I am guilty of this too. Actually, still to this day sometime where I write if some complicated thing return true and then else return false. And then like, oh, crap, I did it again. So another pitfall for programming. So I can do something like that. All right, other function I could write. Maybe I write a function called int length, linked list t. So, oh, link, nice. So if I want to write a function called length, how would I do that? Yeah.
Can I make it recursive?
Sure.
So the base case would be if the linked list head is equal to null.
So base case, if linked list head is equal to null,
Then you return 0.
return 0,
Else return 1 plus length of the linked list, but like with head.
So else return 1 plus the length of the linked list. Uh-oh.
Be like, I think, and linked list head.
Uh-oh.
You have to get the next one.
the next one and give the address to it.
Like the node ahead and then get the next.
So I load the head. So what should I do for that? Anyone help if we want to really do this recursively? Yeah.
You need like another linked list and then make that head.
So I need another linked list, so I can just create it as a local variable. So linked list, let's call it, I don't know, smaller. So I want to change that head, right? So smallers, so in this case it would just be dot head because it's not a pointer right now. I'm declaring it as just a local variable here. So smaller dot head equals link list head next. So I could do something like that. And then for length, I could give it the address of the smaller linked list, right? Make sure all the types go. So yeah, I could do that. It should work. Let's say we compile. Let's make sure this works. So we'll print list. Let's say we print length. And we'll call length of our linked list. And then we'll do it also after removing the node. So if we compile and run this, hey, seems to work. We got length of 4, which was correct, 1, 2, 3, 4. Then we removed a node, said its length is 3. Maybe I should have printed it after we printed the list, but we only have 3 elements now, so this does seem to work. So any questions about that one? This is actually the first time I've ever seen someone want to do it recursively. So that's good. We're thinking recursively, good practice for the final. So other way we could do it, right? If we wanted to do the length function iteratively using a while loop, well, we could just create a local variable called len and just do our normal iterate over our list. So this will probably look very familiar to you. I could say, hey, current's equal to linked list head. While current does not equal null, add 1 to the length, so I know this node is valid. Update current to point to the next. Keep on going until we hit the end of the list, and then I could return len at the end. So we could do it either way. And you could also write is empty in terms of length if you want. This one's probably arguably better, but if I wanted to reuse a function I've already written, I could just actually return if the length is equal to 0. So if the length is equal to 0, that means it's empty. If it does not equal 0, that means, well, it's not empty. Or yeah, it's not empty. It has something in it. All right. So what about if I want to insert a node after another node? So we've just had our function to insert a node to the very beginning. But what about if we want to insert it after another node? So say 3 is currently not in my list, and I want to add it to my list after node 2. So I'll give you a second to think about that, and then we will try to implement that as well. So again, we have node 3, which is not connected to anything, and we want it to be added after node 2, but still in the list. What the hell? All right. Any ideas how I would create a function called insert after? Any guesses? So the arguments would be the node we want to insert. So like this node would be, a pointer to this node would be the node we want to insert. And then we'd have a second argument after, which is the node we want to insert this node after. So after would be equal to 2, node would be equal to 3. Yeah, so here I just have to change 2 things, right? If I want to add this to the list after 2, I have to change 2's next pointer to point to the node I want to add, and then change the node I want to add's next pointer to whatever it was pointing to, right? So if I write my function signature like this, so I have 2 arguments, after and node. So how would I implement this? So there's 2 changes I want to make, right? I want to make the after nodes next. What does that, what should that be equal to? So if I go here, whoops. So in this case, after is 2. What should I make its updated next point to? 3, right? Yeah, so in this case, the order is going to actually matter. I need to change 2 pointers, but so I need to change, whoops. So I actually need to change 2 pointers, right? I need to change this node's next and node 2's next. I don't have to look at any previous or anything like that. So if I wanted to change it, what I would have to do is first, I would update node 3's next to point to the same thing as node 2's, so I don't lose what node 2 is pointing to. If I went ahead and just updated this next pointer to point to node 3 first, then I've lost my pointer to node 4, and I wouldn't be able to get it back. So I would have to do that first, and then I can update node 2's or the after nodes to point to the node I'm just currently inserting. So something like that. So if I went to implement it, I would do after's next node is equal to, well, the node I'm trying to insert, but I would want to do that after. So I want to make sure node's next is actually the same as after's next first, because I don't want to lose that value. So it should look something like this. As long as I've implemented it correctly. So do this, seems to work. Joy to the world. So any questions about what we did there? Next one to think at home or try it after, or we'll take it up in the next lecture. So the next function is something like inserting a node before another node. So